Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, which is dedicated to integral calculus students who are now going through applications of integration, we are going to go ahead and use a numerical method to estimate how far two vehicles have gone in a certain amount of time, and then determine which one has gone the furthest distance. Now, prior to doing this problem, it is assumed that you know the midpoint rule from your Calculus 1 course. There's not much else I need to say about that other than the fact that it is kind of a weird rule when you're using data points. So let's go ahead and remind ourselves of the midpoint rule here. Now, reaching back into our history, we know that the midpoint rule is defined to be the summation from I equals 1 to n of heights times widths, right? You're just doing a Riemann sum, essentially, adding up a bunch of areas of rectangles. But the heights of each rectangle, well, those are determined by the average x value on an interval. And the average is just the sum of the two endpoints, x sub I minus 1 and x sub I, divided by 2. That's an average. So there we go. That's the midpoint rule right there. Well, how do we use the midpoint rule when given a table of data? Well, I should probably read the problem first, honestly. So let me go through and just read that, and then we'll tackle the rest of the problem itself. Racing cars driven by Chris and Kelly are side by side at the start of a race. The table shows each car's velocities in miles per hour during the race's first 10 seconds. Use the midpoint rule to estimate how much farther Kelly travels than Chris during this first 10 seconds. Well, we've read the problem. We know we're going to use the midpoint rule, so we wrote down that formula right there. Now what we need to do is figure out how to use the midpoint rule. Given a set of data, or a set of data points, you're really restricted. If I were to use, for example, right endpoints, and I were to look at all these time intervals here, I would say, okay, well, the right endpoint between time 0 and time 1, well, the right edge of that time interval would obviously be time 1. And then the right edge point between time 1 and time 2, well, that right edge point would be time 2, and so on and so forth. So these would be all my right edge points, and their corresponding outputs, which are the velocities, would be the function values at those endpoints. For example, the function value at time 1 for Chris would be 20. The function value at time 1 for Kelly would be 22, and so on and so forth down the line. Now, suppose instead that we were asked to use left endpoints. Well, the left endpoint between time 0 and time 1 would be time 0. The corresponding function values, by the way, would be 0 and 0. The left endpoint between time 1 and time 2, well, the left edge between time 1 and time 2 would be time 1. And the function values at time 1 would be 20 and 22. And so on and so forth down the line. Notice with left endpoints, you don't include time 10 because the time interval going from 9 to 10, its left endpoint is 9. There's no left endpoint containing time value 10. The midpoint rule is a little bit odd. So notice with the right endpoint and left endpoint methods, we used 10 points, right? Times 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 if you were using left endpoints, or time 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if you're using right endpoints. However, using midpoints, the data is a little more coarse. For example, what is the midpoint between time 0 and time 1? Well, normally I would say time 1/2. That's middle. That's the time between 0 and 1. However, they didn't give me data at time 1/2. So I can't use time 0 and time 1 to find a midpoint in between them. So instead, I'm going to use time 0 and time 2. And the midpoint between time 0 and time 2 would be time 1. Likewise, the next group, or I would say time interval we're concerned with, is the time interval starting at 2 and going to time 4. Well, the midpoint between 2 and 4 is a point we actually have, a data point we actually have, which is time 3. The next time interval we will be concerned with is the time starting at 4 and going all the way to, unfortunately it's way up here, 6. So between time 4 and time 6 is time 5. We have that data point, so we can use it as a midpoint. Between times 6 and time 8, we can use the midpoint for time 7. And between time 8 and time 10, we can use 9 as the corresponding midpoint there. So this is the kind of the oddity with the midpoint rule, is that if you're given data, you have to skip values to get midpoints. And notice the highlighting. We are only going to be using 1, 2, 3, 4, 5 data points, which may seem like this is going to be a less accurate estimation of how far one car is in front of the other. But in the long run and in applications, it ends up that the midpoint rule is a little bit better than the left endpoint or the right endpoint rules. Let's go ahead and use this data along with the midpoint rule to figure out the answer to this question: how much farther Kelly travels than Chris during the first 10 seconds. This actually requires us to remember that the area underneath a function is represented by an integral. So let's just pretend as though this is a function that, let's pretend we have a smooth function there for Chris's velocities. And remember, this is a velocity versus time. Velocity might be in miles per hour, and time might be, let's just pretend, in hours. Then the area underneath this curve right here is going to be, again, height times width. Well, the units for the height are miles per hour. The units for width are hours, and you can easily see the words hours cancel, and we get that the units for this area here will be in miles. So that'll be the total number of miles that Chris has driven so far between these two time intervals. Let's just pretend A and B. It's a great way to visualize or interpret the meaning of an integral. And specifically in this case, because the outputs here are in terms of velocities and the inputs are in terms of time, it should make sense that velocity versus time, we're going to end up with a distance in the long run. So this means that when we use the midpoint rule to approximate the area underneath the curve, what we're really finding is the distance these cars have traveled. So in the long run, what we're going to do is just find out what's the total distance Chris traveled, what's the total distance Kelly traveled, and figure out who traveled farther, and then take the difference to find out how far ahead they are. Let's go ahead and do that here. So notice I wrote m sub 5. It's because I'm doing the midpoint rule with 5 subintervals. Again, 1 subinterval, 2 subinterval, 3 subintervals, 4 subintervals, 5. So we have 5 subintervals, and I'm going to do this for Chris. So that's the notation I'm going to use here. CM5. The midpoint rule for Chris using 5 subintervals. First thing I'll need to note here is, what is delta x? I'll have to ask myself that question. What is the average width of each slice or of each interval? Well, take a look at this first interval here. The width, or this distance here, is actually 2 time units. The width of the next interval is also 2 units of time, and then so on and so forth down the line. I don't have 6 down there, but there you go. So I know that delta x here, or delta t in our case, will be 2. However, it is kind of important, in fact, incredibly important, to note that these time values, let's read the problem, these time values are probably going to be in seconds. So notice the velocities are given in miles per hour, but the time intervals are given in seconds. And that's an issue. So this time value t right here is in seconds. And we'd like to convert that to hours so that we're dealing with only miles and hours, not miles and hours and seconds. So what I'm going to do is convert this delta t, this wiggle in time, which is 2 seconds right now, into hours. So this is 2 seconds, but we happen to know that there are 3,600 seconds per 1 hour. That's 60 seconds in a minute, 60 minutes in an hour. So there's 3,600 seconds per hour. And doing a little simple mathematics here, this would be, let's see, 1/1800th of an hour. That's our delta t. So I'm going to go ahead and trade out this delta x, which actually should be a delta t, for a 1/1800th. And actually, while I'm doing that, I'll trade out these variables here for t's because, well, they should be traded out. All right, so let's go ahead and do that. Now, honestly, once you have that delta t figured out, the rest is just plug and chug. So watch how I do this. I'm going to move that 1/1800th to the outside of this summation. And the summation is just going to add up all the function values starting at the first midpoint and going to the next midpoint and the next midpoint. So if we're dealing with Chris's data here, his first function value is 20, and that's miles per hour, so the units are correct there. His next function value is 46. His next function value is 62. The next one is 75. And finally, the last function value is 86. Close all that up. Remember, everything here is in miles per hour in this group, miles per hour. And this is right here, the number of hours. If you multiply those two together, you should get a number of miles. So in the first 10 seconds, we approximate the distance that Chris has gone to be 0.1605 on forever miles. Now we do the same mathematics for Kelly. Using the midpoint method with 5 subintervals, it's going to be the same delta t, so 1/1800, because the widths of each interval are identical. In Kelly's case, first output is 22. His second output, I say his, it could be a her, is 52. His or her third output is 71. His or her fourth output is 86. And his or her fifth output is 98. And we'll go ahead and add those up. I'm just grabbing a calculator off to the side. And that distance is roughly 0.1827 on forever miles. You could see that actually Kelly is ahead of Chris. Here's Chris's distance. Here's Kelly's distance. You can see that Kelly's ahead of Chris after the first 10 seconds. So the question was asking, how much farther ahead is Kelly? So let's go ahead and just take the difference between those two. And we get that Kelly's 0.02 on forever miles ahead of Chris after 10 seconds, about 2/100ths of a mile ahead of Chris after 10 seconds. Now, the point of a problem like this is really to drive home that when you're working with data sets and the midpoint rule, you're going to have to skip values here so that you have a midpoint. You can't just arbitrarily create a magical midpoint that wasn't given to you. You have to use the data that was given to you and only that data. So when using a midpoint method, you will have to skip values so you can have a midpoint in the center. All right, I hope this was helpful to you. This is not going to be a public facing video because this actually is from the textbook and I would break copyright if I made this publicly available. So this is only private for my students. Anyway, I hope this helps out and I hope to see you in future videos. Have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.